In central force field, today we are going to discuss a very important concept which is called Virial Theorem. Actually, this Virial Theorem is a powerful mathematical tool for analyzing the dynamics of system of particles when the particles or the system is subjected to a central force like gravitational force or electrostatic force, or you may call Coulombian force. Okay. In fact, this Virial theorem has many important applications in physics and astronomy too. And these applications actually include the calculation of the orbits of the celestial bodies, the determination of the mass of galaxy from its rotational velocity, and the study of dynamics of gases and plasma too. So this is a very important theorem. So in this lecture, our aim is to first of all state this Virial theorem and then prove it. And after that, we will see the applications of this very important theorem. So how this theorem is stated, let us see it. For knowing this theorem, let us consider there is a system of particles, and if you calculate the time average total kinetic energy of the system, it means you have to calculate the average value of total kinetic energy of the system with respect to time. Then, according to this theorem, this time average total kinetic energy, which I have denoted by this symbol T bar, this T bar actually represents the time average total kinetic energy. And this is equal to minus 1 over 2 summation over I Fi dot Ri. Here actually this Fi is the force acting on the ith particle, and Ri is the position vector of the ith particle with respect to the origin in consideration. Okay. So you must remember this statement that the time average of the total kinetic energy of the system of particle is equal to minus 1 over 2 summation over I Fi dot Ri. Actually, this quantity minus 1 over 2 Fi dot Ri is known as Virial of Clausius. This quantity is called Virial of Clausius. Okay. So this is the statement of Virial theorem, and you have to remember it because in your examination the statement is also asked. Now we will prove this Virial theorem in a very simple way, starting from the second law of motion. And for this, let us consider that there is a system of particles. These dots actually represent the different particles of our system, and this system I have denoted by this boundary, you can see. And for calculation, let us consider under consideration any particle. We consider an ith particle, and the position vector of this ith particle, as I have shown in this figure, is Ri. You can see. Okay. Now, if you consider that this ith particle experiences a net force Fi, then we can easily write what will be the equation of motion of this ith particle. Okay. According to Newton's second law of motion, you know the force acting on the particle is simply equal to rate of change in momentum. So if Pi is the momentum of this ith particle, then the force Fi acting on it is equal to dpi by dt. And in dot symbol, you can write this dpi by dt simply Pi dot. So Fi equal to Pi dot. This is actually the equation of motion of the ith particle. Now, to prove this theorem, let us introduce a scalar quantity, let us say lambda. So, let us define a scalar quantity let us say lambda, and this lambda is defined by the scalar product of pi and ri, pi dot ri for ith particle. And if you will sum over it for all the particles, then this lambda will be for the whole system. So lambda is defined as summation over I pi dot ri. This is just an arbitrary definition. We have assumed it. Okay. So we have introduced a scalar quantity lambda defined in this way, that lambda is equal to summation over I pi dot ri. Remember, this is a scalar quantity. Actually, as I have told you, that this sum is taken over all particles of the system. Okay. Now we will find the time derivative, or you can say the total time derivative of this lambda. So the total time derivative, of lambda is given by, if you will calculate the total time derivative of lambda, that is d lambda by dt. What will be this? You can see that lambda is equal to this much, and it is a product of two functions. So using the rule of differentiation of product of two functions, we will find this derivative. So this will be what? This will be summation over I pi, that is, this is first function, dot dri by dt. Sorry, here there will be no dot. So after taking dot product, we will write this ri dot. Okay. And plus summation over I. Now pi will be differentiated, dpi by dt dot ri. This is a very simple differentiation. And you can write in dot symbol, this d lambda by dt is equal to summation over I pi dot ri dot. Okay. dri by dt is equal to ri dot, and plus summation over I pi dot dpi by dt is written as pi dot and dot ri. Okay. And let us say this is equation 3. Now we will separately see what is actually the meaning of the two terms in RHS of this equation 3. Separately we will decide it. Let us see here. Now in RHS of this equation, you see the first term is summation over I pi dot ri dot Okay. Now we can write this expression in this manner. You know, this pi is the momentum of the ith particle. So this will be simply the mass of the ith particle and times velocity of the ith particle. If vi is the velocity, then pi will be written mi vi and dot ri dot. Okay. Again, you know that this velocity Vi of the ith particle is equal to dRi by dt, you know it, and this is dot Ri dot, okay. And in dot symbol, you can write it summation over I mi Ri dot, okay. dRi by dt is Ri dot and dot Ri dot, okay, Ri dot. Now this will be actually summation over I mi Ri dot, you know this is Vi dot, so this is Vi and dot Vi. So this is actually the summation over I mi Vi square, and you know this summation over I mi Vi square, this is twice of the kinetic energy of the ith particle, and this will be equal to 2 times of the summation over I Ti. And when you will sum up the kinetic energy of each and every particle of this system, you will get the total energy of this total kinetic energy of this system. So this is simply equal to 2T. Here T is the kinetic energy of the system. T equal to kinetic energy of the system, okay. So what you finally get, therefore you can say that summation over I Pi dot Ri dot, this equals twice of the kinetic energy T. This is 2T, okay. And what will be the equation number? Yes, this is equation 4, okay. So we have simplified the first term in RHS of equation 3 and get that P summation over I Pi dot Ri dot is equal to 2T. Now we will see the simplification of the second term in RHS of that equation. What is the second term? You can see here. The second term is summation over I Pi dot Ri dot Ri. Now let us simplify it. Okay. So again, we will simplify summation over I Pi dot, there is Pi dot here, a dot Ri, okay, Pi dot Ri. Now as you have seen in the first equation when we have written the equation of motion, that this Pi dot is equal to Fi. So you can write this expression as Fi dot Ri, okay. Here we have used the first equation where Pi dot is equal to Fi. This is net force acting on the ith particle, and say this is equation 5. Now we will substitute the values of these quantities which we have obtained here in equation 4 and 5 in equation 3. So equation 3 is now written as, how we will write equation 3, you can see easily. See the equation number 3 here. This is d lambda by dt equal to this and plus this. Now we will substitute the values of both of the quantities in RHS of this equation, and then you will get that d lambda by dt, and instead of the first term we will write actually 2t, and at the place of second term we will write summation over I fi dot ri, fi dot ri, okay, fi dot ri. Say this is equation 6. Now our aim is to find the average value of this kinetic energy for which is kinetic energy of whole system for a given time interval. So let us consider we want to find the average value between a time interval of 0 and tau. Let us consider. So you can say the time average of equation 6 over a time interval tau is given as since we are going to find the time average for the time interval tau, so what will be the average value of this d lambda by dt for the interval tau? This will be simply 1 over tau integral 0 to tau d lambda by dt, okay, and this 2t, we will take the average value of this 2t, this is average value, and plus the average value of summation over I fi dot ri. This bar, the sign of this bar actually represents the average value, okay. Or you can see this integral will be what? This integral can be written as, this is simply lambda of t at tau and 0, okay, and this equal to average value of 2t plus average value of summation over I fi dot ri, okay. I think you are getting the things. Now when you will substitute the limits, what will be the terms in LHS? This will be 1 over tau lambda at time tau minus lambda at time 0, okay, lambda at time 0, and this will be equal to average value of 2t plus average value of summation over I fi dot ri, fi dot ri. Say this is equation 7. Now you can see if we consider the periodic motion, then this time tau may be taken as the period of that motion. And if tau is the period of motion, then all coordinates repeat after this time tau. And when when the coordinates will be repeated, then actually this lambda tau and lambda 0 will be equal, because during a periodic motion, after the time interval equal to its time period, the every quantity is repeated. Okay, so particularly in case of periodic motion, first of all we see what will happen. So in case of periodic motion, if we particularly consider periodic motion and assume that this tau is equal to time period, tau equal to time period, if we consider, then we know that in case of periodic motion, this lambda tau and lambda 0 both will be same. Okay, and therefore the quantity in the LHS of this equation 7 you can see will vanish, it will be 0. And so in this condition you can say that this 2 average value of 2t plus average value of summation over I fi dot ri, fi dot ri, this will be equal to 0. This is equal to 0, and this implies that average value of 2t is equal to minus average value of summation over I fi dot ri. Okay, and therefore what will be the time average of kinetic energy of the whole system? This will be minus 1 over 2 summation over I fi dot ri bar. Okay, and see, this is nothing, this is simply the statement of the Virial theorem. Okay, and as I have told you that this quantity in RHS of this equation A1 is known as Virial of Clausius. Okay, actually this result we have obtained considering that the motion is periodic, but you will see that this result or this theorem also holds when the motion is not periodic. Even in non-periodic motion this result holds, but when this result will hold if the motion is non-periodic, you can see if we consider that the motion is non-periodic and the coordinates and velocity of all particles remain finite, so definitely there will be an upper bound quantity lambda. It means lambda will have a particular maximum value. And so in this condition, by taking the time tau very large, the left hand side of this equation, that is lambda tau minus lambda 0, that may be made is very small, that is smaller and smaller, and consequently you can say that this quantity may be reduced to 0. Okay, so you can say this result also holds in case of non-periodic motion although we have obtained this result for periodic motion, but it is valid in case of non-periodic motion too. Okay, but when this will hold, you can see if tau is very large, tau is very large, okay, then this lambda tau minus lambda 0, okay, will tend to 0. Lambda tau minus lambda 0 will tend to 0 because this tau, this lambda tau, or you can simply say that lambda has a definite upper value. So in this condition, when tau is very large, we can make this quantity smaller and smaller, and consequently it may be equal to 0. So in that condition, you can say this result will again hold. Okay, and therefore in this condition, equation A1 holds even in non-periodic motion, even in case of non-periodic motion. Okay, so you can say that Virial theorem is valid both for the periodic motion and also for the non-periodic motion. Okay, now particularly we will see what will be the form of this Virial theorem when the system of particle is under the central force field. So Virial theorem in central force field. What will be its form in this condition? Let us now see it. Now consider only one particle, not a system of particles. We simply consider a single particle, and this particle is moving in a central force field. And the force acting on this particle, let us say, is F. This is actually the central force, and its position vector is equal to R with respect to the center of force. Okay, so consider a particle moving in a central force, okay, moving in a central force. And in this condition, if you will apply the equation or the Virial theorem, then what will be the form of that Virial theorem? You can see. Then T average, this is actually the kinetic energy of this single particle, average value of kinetic energy, and this will be written as, according to Virial theorem, T bar equal to 1/2 F dot R. Okay, here F is the central force acting on the particle. F equal to central force acting on the particle. Okay, now you know that if V is the central potential. Central potential, or you may also call it potential energy. Central potential or potential energy of the particle. Then you know that the central force is given by the negative gradient of the potential energy. Okay. So then F is equal to what? You know, this is minus del V by del R times R hat. This is just the relation between central force F and the potential energy V. So now let us replace this F in this equation by this expression. So you can write the time average of kinetic energy of this particle will be equal to what? This is actually the average value. So write here the sign of over bar. So this will be equal to what? This is minus 1 over 2 and minus del V by del R and R hat dot R. Okay. And for average we write here the sign of over bar. Okay. Now see, since this vector R is equal to R times R hat, okay, R times R hat. So R dot R hat, this will be simply equal to R, okay, R dot R hat, this will be R times R hat dot R hat, and R hat dot R hat, you know, it is equal to 1. So this is simply R. So this time average of kinetic energy, you can see, is equal to, now this minus minus will be plus, so this is plus 1 over 2 del V by del R times R. Okay. And for average we write this sign of over bar. Okay. So this is the form of the Virial theorem in case of central force field. Okay. And let us say this is equation number 8. This is equation 8. Okay. Or don't write it, but say this is equation A2. You can say that this is Virial theorem in case of central force field. Equation A2 represents Virial theorem in case of central force field. Okay. Now you know that the potential energy function in case of central force field is definitely a function of R. But what will be the power on R in the expression of potential energy? That depends on the nature of the central force. Now, for example, let us consider V equal to a constant C at times R to the power n. Not n, but for simplicity we take n plus 1. Let us consider. Okay. If you consider that V is equal to a constant C into R to the power n plus 1, where n is any number, then what will be the average value of kinetic energy? You can see then T bar will be equal to, you have seen that this is equal to 1 over 2 del V by del R times R average. Okay. Now as we have assumed that V is equal to this much, so let us substitute it. 1 over 2 del R CR to the power n plus 1 average times R. Okay. And now this is a very simple differentiation. You can do it. So let us see what will be the result. This will be n plus 1 over 2 C R to the power n times R. R to the power n times R. Okay. And average of it. And this can be written as T bar equal to n plus 1 over 2 times C R to the power n plus 1 average. Okay, average. And as we have assumed that this V is equal to CR to the power n plus 1, so in place of CR to the power n plus 1, we will again write V. And therefore, finally, you can see that this T bar is equal to what? This is equal to n plus 1 over 2 times V average. So if a potential function depends on R by like this equation, then the kinetic average value of kinetic energy of the particle is related to the average value of potential energy by this equation. T average is equal to n plus 1 divided by 2 times average value of V. Okay. Now, let us particularly consider the case of the inverse square law force. In case of inverse square law force. You know, if the force is inverse square law, then F is equal to C over R square, that is C times R to the power minus 2. And you also know that in this condition, the potential energy function is equal to C over R. That is, this is C R to the power minus 1. So in this condition, what will be the value of n? Since in general result we have assumed that V is equal to C R to the power n plus 1, and if particularly we consider that our central force obeys the inverse square law like gravitational force, like Coulombian force, in that condition you know that potential energy function is equal to constant C times R to the power minus 1. So at the place of n plus 1 here, now we are considering particularly minus 1. So you can write in this condition n plus 1 is equal to minus 1. N plus 1 equal to minus 1. So what is the value of n in this case? N will be minus 2. So particularly in case of the central force obeying the inverse square law like gravitational force, Coulombian force, n will be equal to minus 2. And if n is minus 2, then in such case, what will be the average value of kinetic energy in terms of, sorry, the page has been turned, but this will be okay, just see here. This is just a moment. See here. We will simply substitute n equal to minus 2 in this equation A3. So from A3, what will be our result? You can see the average value of kinetic energy is equal to what? This is n plus 1 over 2 times average value of potential energy. Okay, and as we have seen that in case of the central force obeying the inverse square law, n is equal to -2. So T bar is equal to -2 plus 1 divided by 2 times V bar. That is, you can say this T bar is equal to what? This is -1 over 2 V bar. Okay. So in particular manner, if you state the Virial theorem in case of the central force obeying the inverse square law, then you have to say that the average value of kinetic energy of the particle is half of the average value of potential energy. Okay, this is Virial theorem, particularly in case of the central force obeying the inverse square law. Okay, I think you have understand each and every step because this was a very simple calculation. And as I have told you that this Virial theorem is very useful and it has so many very important applications in physics and astronomy. And these applications actually includes the calculation of orbit of the celestial bodies, the determination of the mass of the galaxy from its rotational velocity, and the study of dynamics of gases and plasmas. Okay, so this is a very important theorem. So this theorem is very important and it will be used in calculation of different things as I have told you. So we will see such applications in the forthcoming lectures.